Hi, Blue Dot, how's it going? Is everybody excited for New Order later? Woo! So yeah, thank you so much for coming. I know it's one of the last talks on the last day, so we're going to take it nice and easy. I'm going to talk to you about the violent birth of stars. So I am a radio astronomer here at Jodrell Bank, at the Jodrell Bank Centre for Astrophysics at the University of Manchester. And I am interested in how stars like our sun formed. It's one of the most fundamental questions: how did we get here? We can't really go back in time and look at our own sun and see what happened. So what astronomers do is we look at the birth of other stars in neighboring star-forming regions, and we sort of use them as a type of time machine to replay the events that created our own solar system. And we do this using both ground and space-based telescopes. Now, I'm sure you've seen a version of this graphic several times this weekend, but I just want to quickly remind ourselves of the electromagnetic spectrum. We know that light comes in many different types, which we characterize by wavelength. So we have long wavelengths at the one end, and the wavelength is just the distance between two crests of the wave. So the longer wavelengths are the radio waves at my right, your left. The shorter wavelengths are down here at the gamma rays. But the human eye is only sensitive to a very narrow range of wavelengths, which we call visible light. But most objects in our universe radiate at wavelengths that our eyes cannot see. So we have to build instruments that have detectors that are sensitive to these other types of wavelengths in order to study the objects in our universe. So probably the most famous telescope that has been used to study young stars is the Hubble Space Telescope, which observes at infrared, visible, and ultraviolet wavelengths. And different measurements of light are really important for studying objects in our universe because they allow us to determine certain physical characteristics, such as temperatures, compositions, velocities. X-rays have much shorter wavelengths. So the example shown here is that the wavelength is about the width of a water molecule. The Chandra X-ray Observatory is the X-ray version of the Hubble Space Telescope, and it's space-based because our atmosphere is opaque to X-rays, which is really important for protecting life here on Earth. So we have to send telescopes up into space if we want to detect X-rays from objects in our universe. Objects such as supernova and really extreme environments produce X-rays, where the temperatures can reach up to millions of degrees. So radio waves and microwaves are at the long end of the electromagnetic spectrum, so they have much longer wavelengths than infrared light. They can range up to meters in wavelength. Because they have such long wavelengths, they have much lower energies, they indicate much lower temperatures. So they're usually found kind of permeating everywhere in our universe. They're in the background radiation of the universe, they're in cold interstellar clouds, cool remnants of supernova explosions, to name a few. But what's so awesome about radio waves, and the reason why they're so long, and we can detect them here on Earth, so we don't have to send radio telescopes up into space. We have this nice radio window ranging from centimeters to meter wavelengths where we can very easily detect radio waves from space. So one of the nearby star-forming regions that astronomers observe is called the Carina Nebula, and this is located in the southern sky. So the telescopes here are located in Chile, and you can see a treasury of deep sky objects in our Milky Way. And the most obvious of these is the Carina Nebula, which is the bright red glowing cloud in this image. So it's in the constellation Carina, which is the keel of a ship, and it's located at almost 8,000 light years from Earth. It is a cloud of glowing gas and dust and is the brightest in this image and indeed in the southern sky. It contains several of the most massive and brightest stars in our galaxy, and it offers a perfect laboratory for astronomers to study the birth and death of stars. So I'm going to cheat a little bit and play a quick video to get an idea of some of the scales involved that we're talking about. So we're going to zoom into the area of the constellation where the nebula is. And as we zoom into the cloud, we begin to detect lots of really fine structures in the nebula. And we'll look at these in a bit more detail in the next couple of slides. But as we slowly zoom in, we're honing in on a region that we call Mystic Mountain, because indeed it's very beautiful, it's very fantasy-like. It's made up of dense pillars of gas and dust, shown first here in visible light, and next in infrared light. Thanks, Isa. Right, so now let's take a closer look at this nebula in visible light. The nebula is a cold cloud. It's made up of mostly hydrogen gas. It is laced with dust, which makes the cloud opaque, and this makes it very difficult to actually observe star formation within this cloud, because whatever is going on is often hidden behind the dust. However, as the matter collapses due to gravity and it forms these clumps in the cloud, the dust begins to heat up, and it causes it to radiate in the infrared portion of the spectrum. And so this often indicates to astronomers that there are newborn stars inside. But there are also loads of other interesting features in this cloud. And you're probably wondering, when are we going to get to the violent bit of star formation? Because this looks very serene, it looks very peaceful. But there is a lot going on. So over here on the far side of the nebula is Eta Carina, and it is a star. It's very massive. I think it's over 50 times the mass of our sun. And it's on the brink of a supernova explosion. So you can imagine there's loads of energy, extreme temperatures over here in this stellar nursery. Also, these bright stars in the middle here, they're also very massive, and their UV radiation is blowing out these huge winds, and it's causing this cavity to form in our cloud. So there's a lot of extreme temperature going on, a lot of extreme radiation. Is this helpful? Does it hurt star formation? What you can see is the ridges on the edge. Every clump you see probably harbors a new forming star. So let's zoom in on one of these regions again. Here's Mystic Mountain. And to be honest, if I was the astronomer that took this image and saw this for the first time, I probably would have squealed, because you see these huge jets just shooting out of this cloud. What could be causing these jets? It's really hard to tell from images made in visible light, because whatever is shooting out these jets is hidden behind all of that dust. So we need to go to longer wavelengths in order to penetrate through that dust, in order to find out what's powering these jets. So that's why it's really important to observe at several different wavelengths along the electromagnetic spectrum, because they can offer very different but complementary views of the same object. So observations at infrared allow us to peer through. We can begin to see some of the newborn stars within these dense pillars. They're heating up and glowing in the infrared. But Mystic Mountain is a stellar nursery, so these jets must be linked with star formation. But how? So from all of these different types of observations, we can begin to piece together the puzzle of star formation and how stars like our sun were born. And what we begin with is a giant, very cold, slowly rotating cloud, which begins to clump, and it begins to collapse due to its own gravity. And so as it collapses, we form these sort of clumps that are going to begin to become newborn stars. Because of the rotation and movement within the cloud, there's some spin involved, some angular momentum, which is one of those properties that has to be conserved. So the clumps, they're collapsing due to gravity, but the material and the gas and the dust within those clumps, in order for them to go into the star, they first flatten into a disk, and the disk rotates, and the central object inside our newborn star, it begins to feed off of that gas in the disk. And what happens when that happens is that it begins to speed up. As it continues to gobble the mass surrounding it, it spins up, almost to the point of breaking. And so this isn't going to help us form a new star. So what has to happen? It needs to slow down. And the best way for it to slow down is to shoot out these supersonic jets of material. So if you think of a really simple analogy, such as an ice skater or a ballerina, when they're spinning really fast, they make themselves really compact, and they spin and they rotate faster and faster. But when they slow down, what do? They stick out their arms. these stars are doing the exact same thing. They're ejecting these supersonic jets of material in order to slow down and spin at a rate that will allow them to consume the material around them, that will allow them to grow and develop and become systems like our own. These jets are very easy to see. Oftentimes, they're the first thing we see that indicates that there's a newborn star inside. However, there are still many questions about these jets. We still don't know exactly how they're launched, so it's still a very active area of research. But once the star has finished growing, once it's finished consuming material around it, you're left with a disk, and the disk eventually dissipates and planets form in the disk. And you begin to see solar systems like our own. So there are some scales on here. AU means astronomical unit, which is the average distance between the Earth and the Sun, and astronomers just use it as a much easier way of describing distances. In miles, that's about 93 million miles. So these are very large-scale systems from the beginning. And then our solar system is about 80 AU in diameter. Right. So let's take a closer look at these jets, because they're my personal favorite thing. So the most striking feature to me in Mystic Mountain is this 3.5 trillion mile long jet. It's being blasted into space by a newborn star, which is hidden in this clump of material at the top of this pillar. The jet is traveling at hundreds of miles per second. So think if you got from here to London in about 1 second. That's how fast these jets are traveling. And because they're traveling so fast, they're plowing through the interstellar medium. You can see these incredible bow shocks at the end. So if you think of a ship on water, and as it moves, it creates this bow shock. As these jets move through dense material in the cloud, they create these bow shocks, and especially if they're impacting on clumps within the cloud. Right. So to illustrate better what I'm saying, I've overlaid our model. Our protostar is hidden within the envelope. As it accretes material that is spiraling around it, it travels faster and faster. In order for it to slow down, it shoots out these jets in order for some of that material to stick. And this is really important because it tells us the history about these stars. You can see that there are clumps of material in the jet, and we think that the accretion process is episodic. So it gobbles up a bit, ejects out a bit, gobbles up a bit, ejects out a bit. So that tells us, you can almost see the formation history of this star. It's like looking at a baby photo album. So here are a few different looks at similar stellar systems, where you can very clearly see the disks, and then the jets are perpendicular, removing some of that excess angular momentum. Right, so we have some more videos. Hubble, because it's been operating for so long, has been able to look at some of these jets over several years. So there are about 14 years of history of this jet. Remember, it's traveling at hundreds of miles per second. So when that happens, what happens when you're traveling that fast? You're going to crash, right? So that's why we can see these bright knots of emission heating up and glowing, is because the jet is effectively slamming into itself. Each clump that's ejected is traveling very fast. It shocks against what's in front of it. It heats up and glows, and that's how we're able to see it. Here's another example where another long, narrow jet has burst out of this cloud. So over here, our newborn star is hidden. It's obscured by all of this dust. We can see the scattered light coming out of the disk and the nebula, but we see the jet sort of wiggling across down here. It's got a really bright bow shock where it must have impacted against something. It's probably slammed against another bit of the cloud. But something else that's funny about this jet is it does have these wiggles. So what astronomers think is happening there is that maybe there isn't just one newborn star inside. Maybe it's a binary system, and because of the interaction between the two stars, it's causing this jet to precess and wiggle. So we can get a lot of information from these jets. So here's one of a bow shock at the end of a very large jet. It shows it shocking against bits of the molecular cloud that it's being ejected into. And you can also see bits within it that are heating up and glowing, and that's because it's also slamming into itself. So these are very violent environments. So what happens after the star has finished consuming material from around it? The jets turn off, and we're left with a dusty disk. And this is where we begin to see signs of planet formation. The disk begins to dissipate, and planets begin to carve out rings in the disk, and they're also consuming that disk material and growing from that. And that's how a new solar system is born. And we're beginning to routinely detect these disks. These are all from the ALMA telescope, so the Atacama Large Millimeter Array down in Chile. And you can see that simulation was actually quite accurate to what we are detecting from these young stellar systems. The high resolution offered by these telescopes is just, it's always improving. We're always zooming in closer and closer to see what's happening. So I'm going to switch gears a little bit. There are other types of objects out in the universe that have jets. You may have heard a few talks this weekend on black holes. Pulsars are a very popular topic here at Jodrell Bank. But supermassive black holes at the centers of galaxies also have these huge jets that they eject. They travel much faster than jets from young stars. They reach relativistic energies and velocities, so close to the speed of light. And this particular image is of the peculiar galaxy Centaurus A. And it's a composite image of visible, radio, and X-ray wavelengths. So we're going to break it down. So here is Centaurus A at visible wavelengths. And you can kind of see why they call it a peculiar galaxy. It almost looks like a spiral galaxy, like our Milky Way, with this dusty disk across the middle. But it also has a sort of spherical, elliptical glow around it as well, which is characteristic of elliptical galaxies. And so what astronomers were able to piece together from these kind of images is that perhaps these are two galaxies that have collided in the past, and that's why it's quite peculiar. So what do we see at very long wavelengths? So this radio image was taken with the Very Large Array at wavelengths of about 6 centimeters. And it reveals an outflow that was invisible at optical wavelengths. You can see the pair of narrow jets shooting out from the middle, and then it's got these huge diffuse plumes. These are radio jets that consist of plasma, and they're a high-temperature stream of matter in which atoms have been ionized and molecules have been split apart. So at much shorter wavelengths, here in the X-ray, you can see a much different picture. It's much more extreme, much more violent. And these provide additional evidence that there is a supermassive black hole at the center of this galaxy powering these jets. You cannot see a black hole directly. I think we all know that by now. So these jets are really important indicators that there are supermassive black holes at the centers of galaxies, which are like young stars. They're consuming material from a disk around them and ejecting these huge jets. So studying young stars, they're much closer to us than black holes are, but they can help us shed light on this jet mechanism, which spans huge orders of magnitude in energy and spatial scale regimes. So there's jets coming from all different types of objects in our universe. I think studying young stars is really important in order to help solve many of the questions that we have left still when it comes to jets. Oh, and here's the composite image again. And just to give you an idea of the spatial scales of this on the sky, I saw this image on the astronomy picture of the day, and I just thought it was really cool because it's massive. So I'm going to switch gears a little bit. I'm going to talk a bit about my career as an astronomer. I know we have a lot of enthusiasts here. Maybe there are some young folk who want to know what the career path looks like, but I'm also going to show you some radio observations that I've taken along the way of protostellar jets. So this is me back in 2008. I was doing my bachelor's degree in physics, but I was very lucky to be able to intern at NASA's JPL Jet Propulsion Laboratory in California. And this is really what kick-started my career. This is where I fell in love with research. It's where I fell in love with space exploration. I got to watch them build the Mars Curiosity rover. One of the Mars rover drivers calls him George because of Curious George, so I call it George now. Then in 2010, I moved to Ireland to do my PhD, because if you want to do a career in astrophysics, you need a PhD. So I was studying at Trinity College, but I did most of my research at the Dublin Institute for Advanced Studies, which was located in this beautiful Georgian building. And then I used to give this talk at Dunsink Observatory, but to a much smaller audience. So one of the star-forming regions that I was looking at is called L1551. It's just a catalog name. It's quite boring. But it's located towards the Taurus molecular cloud in the constellation of Taurus. And you can see many different objects in this image. They're all young stars. There's a bit of a nebulosity up here, but down here, you can see the outflows coming from NE, which is just northeast. IRS5 just means infrared source 5 in this group of stars, and it's got this huge outflow. You can see lots of shocks within this jet. And this is an infrared light, near-infrared wavelengths. So if we zoom in on infrared source 5, or IRS5, we can learn a lot from this image. The astronomers who published this paper, Hayashi and Pyo, identified 2 jets coming out of this stellar system. So it's very obscured. You can sort of see where the disk and envelope is obscuring the system. There's a lot of scattered light coming out, but hopefully you can see 2 green jets coming out of that area. So the problem with this type of observation is we're not really able to zoom in to where those stars are being formed. We can see the jet on larger scales, but we need to zoom in a bit closer, and we need to go to longer wavelengths in order to do that. So this is me jumping for joy on my first observing trip. I was very lucky to go to the Giant Meter Wave Radio Telescope in India. These are 45-meter dishes, so they're not quite as impressive as the Lovell Telescope, but they're quite impressive in their own right. And because this was my first observing trip, I had my own expectations. I thought I was going to be able to chill out. I was obviously misled by movies. This is the Very Large Array in New Mexico in the movie Contact. Jodie Foster, very calmly relaxed, listening to her observations from the telescope. I got to sit behind a computer and stay up all night instead. We don't really get to listen to our observations when we're studying young stars. I've never seen my slides this big, but you can see the bags under my eyes from being up all night. But right, so this is my first observing trip. We're observing at meter wavelengths here, so very long wavelengths. This was the first time we had ever looked at these young stars at such long wavelengths. So what does the sky look like? So this is the result of that observing trip. This is towards that L1551 region. You can see lots of objects in the sky. This is our field of view. So as you go out from the center, the sensitivity decreases. We have nice sensitivity in the middle, which is where our young star is supposed to be. But this is about 1.5 degrees across the sky. So let's zoom in a bit to a much quieter region. Each one of these bright spots that you see, they're not stars. Those are galaxies. Other than our own, the brightness is produced by those supermassive black holes at the center of galaxies. Some of them are resolved enough that we can actually see their jets, those big, beautiful radio jets that we talked about a few slides ago. This one's quite characteristic. The supermassive black hole must be in here with a disk, and it's shooting out these jets. This is a bit funkier. I don't really know where it would be here. Maybe the black hole is here, and there's some sort of something in the environment that's deflecting the large-scale jet. But neither of these were my young star. My young star is here in the noise. You can't really see it, so let's zoom in. Not as exciting, is it? So let's change the brightness a bit. Let me describe this a little bit. So I've put this ellipse down here, which indicates the resolution of our observation. So this is about 1400 AU for the distance of this object. So this ellipse is about 17 times the size of our solar system. And what this means is that this determines the resolution of our observation. So if you think about it like a pixel in a camera, you can't really get much information on scale smaller than a picture. We can't get that much information on scales smaller than this ellipse. So that's why it just looks like a big blob. It's not very exciting, but it is a detection, and it was the first detection of a young star at 1 meter wavelength. So if we compare it to those infrared observations, you're not really getting that much information. The resolution is not really good enough to get into that obscured region where those stars are being born. So how can we get past that? Well, we can observe at shorter wavelengths, which gives us an improved resolution if you're not changing anything else about your telescope. So here we have an observation about 9 times, with a resolution about 9 times the size of the solar system at the distance of this particular object. It's looking a little better. If we throw some contours on there, we're beginning to detect some structure. And if we compare it to those infrared observations, we're beginning to detect those jets from that young star. So even though at meter wavelengths, this resolution may not be that impressive, this is really important in the lead up to the SKA, which will observe young stars from wavelengths beyond a meter up to a few centimeters. So this is a pathfinding project. This is a very large array observation of the same object, so it has a much higher resolution, 25 AU instead of 700. And you can begin to detect the binary system hidden within. So that's at 3.5 centimeters. So with eMerlin, what we hope to do is we hope to zoom in even more. We'll only be able to detect some of the brightest young stellar systems with eMerlin because it's only 7 telescopes across the UK, so the sensitivity isn't really there to detect the fainter star-forming regions. But it does get down on the same scales as the Hubble Space Telescope, but it can peer through all that dust that Hubble cannot see beyond. So that's our next step. And then with the Square Kilometre Array, if you were here for Keith's talk just before mine, you'll know that they're going to try and look in and peer on these newly forming solar systems, detect planets, zoom into the very center of those disks, and learn more about the cradle of life from where we came. And then we'll have much better sensitivity. It'll allow us to really see the really faint objects in our sky and hopefully solve the question about how are these jets launched. We think it has something to do with magnetic fields, but where those magnetic fields are connected, how they're throwing out material, it's still an active area of research. So we hope that the Square Kilometre Array will answer a lot of these questions for us. So just quickly before I wrap up, if you want to learn more about star formation, I am in the Museum of Science and Media in Bradford. I've got a little clipboard where I answered some questions from school kids about star formation. I'm hanging out next to my pal, the Lovell Telescope. So the Hello Universe exhibition is going on until January, so pop by if you can see it. I've also done a TEDx talk where I've talked about research culture and what it's like being an academic. So if you're interested on that side of things, it was at TEDx Macclesfield, so very local. It was a really amazing event. You should check out all of those talks. And I will end it there and open it up for questions. Thank you so much.
All right, thank you, Rachel. Great talk. Any questions? We've got some mics going around. Stick your hand high in the air.
Can I actually do something really cheeky before everybody runs away? Can I take a photo? Do you mind? You've been amazing, and this is the biggest crowd I've ever spoken to. Say cheese! Woo! Sorry, questions.
How long would it take for a star to be born from like the clouds like coming together and starting to heat up to getting a star similar to our sun?
Yep. So it's on millions of years time scale. So our solar system is about 4.6 billion years old, and so the stars going from cloud to sun takes about a few million years.
Hi, thanks for the talk. Do we know how conditions need to change to produce different sorts of stars, sort of different within the main sequence of stars? How different conditions need to be to produce different sorts of stars?
Sorry, I couldn't really hear that. Could you ask that again? I'm really sorry.
Sorry. I was just wondering how different stars are formed from different conditions.
Right. So yes. So there are a lot of molecular clouds here in our own Milky Way. There are some cold, quiet clouds nearby. So like the Taurus molecular cloud is where we have a lot of stars that are similar to our sun are born. They're very low mass. The Carina Nebula that I showed at the beginning, as you saw, it was quite extreme, and that usually gives rise to much more massive stars, because those are what are ejecting all of that extreme temperature, extreme radiation, and that can feed back into the cloud because it can trigger some of the clumps within the cloud to collapse and form protostars, but it can also hinder star formation. So if you have all of that extreme radiation going by, it can also halt a star from being born. Does that answer your question a bit?
Hi, yeah, my question was, the structure right early on, was it called a castle? Was that the name of it?
Mystic Mountain?
Mystic Mountain, sorry, yeah. What was the scale of that in astronomical units? Just give me an idea of how colossal the thing must be.
So that image, let's see, it might have a scale bar on it. It does not. So I know that this image, I think it's 50 light years wide. So zooming in on that, I'll let you do the math. Are there any ladies who have any questions or any kids? Okay, sorry.
When we talk about, can you hear me? When we talk about stellar nurseries, it seems that there's loads and loads of stars that get produced in one kind of area. But when we talk about the formation of our solar system, it seems that we focus on just the one star. How many nearby stars were formed in the stellar nursery that produced ours, and kind of over what time span?
That's a really good question, and one that I don't have on the top of my head. So we do feel a bit isolated, don't we, our sun? I don't even remember the closest nearby star is like something 4 light years away or something. Is there an enthusiast in the audience who knows? Yeah, nice. I've already lost track of what your question was. Are you saying the sizes and timescales for our own stellar nursery? So they will be similar to what I've talked about. They'll form on timescales of millions of years. It's possible that there were much closer stars to us, but during the formation, if stars get too close, they tend to push each other away. So what happens a lot we see a lot of binary systems. We see that a lot of stars form in multiples. But we almost never really see them in threes, because what will happen is the system will become unstable. Usually somebody gets kicked out because three's a crowd. But yeah, don't know if that answers your question, but it's quite similar to what I've presented in the beginning.
Hi. Yeah, I was just wondering, I read an article the other week about the Great Attractor, and I was just wondering if it has anything to do with the birth of stars.
The Great Attractor. I haven't heard that. Do you want to come talk to me afterwards and you can show me that headline? I can't actually see where you are.
Back right. Back right. Yeah, just talk.
I'll come speak to you later.
How old does a star have to be to hold a planet, like a solar system?
Yep, a few million years old is when it starts. So let's see. So it has to go through all of this before it becomes a solar system.
Another one at the back.
How many solar systems have people found?
How many solar systems have people found? So we're detecting new planets all the time. Most of them, because technology is always improving, we haven't quite got to this stage yet where we're able to detect solar systems like our own. So right now we're really only detecting, Jupiter-sized planets that are really close to other stars. We're beginning to detect, I think, closer and closer to Earth-sized planets. But I don't think quite yet we've detected in another solar system quite like our own. I think we're still quite unique in that. But hopefully the new telescopes coming online will help us detect more and more solar systems like our own.
Hi there. In the next sort of 5-10 years of your career, what are you most excited about in your field of research?
I think I'm obligated to say the Square Kilometre Array. It's kind of, when I first started my PhD and I started taking classes, we were really gearing up for the Square Kilometre Array. It was going to be, the next generation radio telescope. It's going to answer all of our questions. It's this huge technology. And so we've sort of been directing all of our science questions to what will we see with the SKA. So a lot of my past projects, a lot of my current projects, it's basically building up to what we're going to see. We're hoping to zoom in further and further, closer and closer to the star to help solve some of these fundamental questions about how these jets are launched and how stars like our sun is formed. So I'd be most interested to see what the SKA produces when it comes online in 5 to 10 years.
Hi. What actually causes the dust and gas in the nebula?
It's just around. So, I'm not sure if you were in here for Keith's talk before, but he went through a diagram of the Big Bang. So basically from the beginning of the universe to where we are now. When you had the first stars and they exploded in supernova, they created all of these elements, all these different gases. This all eventually forms and clumps together, and that's kind of where you get all of the clumps of different gases and different dusts to make their own galaxies, and then star-forming regions within those galaxies. It helps when you have a lot of feedback in your galaxy. So supernova explosions is a big one. Jets from various different types of objects feed back a lot into these clouds, giving a lot of elemental abundances and gas and dust.
Hello. Is star formation ongoing in our galaxy at the moment, or are we very well established?
Oh, it's definitely ongoing, and we can really only observe it in detail in our own galaxy. Because it's happening on such small scales, we're able to see it with our telescopes, but we wouldn't actually be able to observe it on those fine scales in other galaxies. So what a lot of telescopes do is they measure sort of general characteristics of other galaxies to sort of get a star formation history of those, but it's only in our own galaxy that we're able to see those details.
Hi. You showed a diagram showing the 6 phases of the star formation. You had it on the screen just a moment ago. I'd be interested to know at which of those 6 stages the star actually ignites.
Yeah. So it's the last stage. I only show it up to when it ignites. So that's when you start hydrogen fusion. That's when it becomes a main sequence star. But up until then, it's not switched on.
And how quickly does the ignition actually happen? How suddenly?
I wouldn't. It takes millions of years for it to happen. So I'm just going to say not very suddenly.
Okay, thanks.
Is it possible to have planets that have 2 suns?
Sorry, I couldn't quite hear that. Can you say that again?
Is it possible to have planets that have two suns?
Yes, it is. I haven't personally observed any, but it's definitely something that can happen. Are you thinking of, is it Star Wars?
Any more questions? Great to have so many questions. Oh, no, there's one at the front.
One more?
Do you want to?
It's going to be a tough one, I know it.
No, hi, great talk, but I'm really interested in jets. And is there any way of actually measuring the angular momentum of the stars? Because you said the jets are to reduce the angular momentum.
Yep.
Can you correlate that?
Yep, so all you need to measure the angular momentum is you need the mass, you need the rotational velocity, and the size scales involved. So because these are so nearby, we are able to measure those characteristics and determine those physical properties. Great question.
Another one here at the back.
How long till our planet's sun explodes?
Was that a how?
Yeah.
How does our sun explode?
How long?
Oh, how long? Right. So we're about halfway there, actually. So in another 4.6 billion years, our sun will not explode. Our sun will expand into a red giant star, and that will consume Earth. I think we'll all be long gone by then anyway, so we won't really notice. But stars like our sun won't actually explode in a supernova. They're too small. So you need stars that are about 8 times the size of our sun to explode in a supernova.
Okay, I think. Oh. Yeah.
Are binary star systems formed in the same way as the ones that, like, our sun was formed?
Primary star systems?
Binary.
Binary star systems, yes. So what will happen is if you have a binary system, each will have its own disk that it's consuming material from and growing from. And sometimes you can even find those in an even larger disk surrounding both of them. So it can get quite complicated, but it does happen. We more often detect binary systems and multiple stellar systems than we do isolated stars.
Okay, I think we'll wrap it up there. And another huge round of applause for Dr. Rachael Ainsworth.